Welcome to the second episode of Delving into Academics. It's a podcast where researchers from physics, biology and chemistry are all interviewed about what they're currently working on and their life as an academic. In this episode, we're interviewing Professor Colin Pulham and his work in high pressure chemistry. He's also the head of the School of Chemistry as well. So I hope you enjoy. So today I am here with Professor Colin Pulham. He is a professor of high pressure chemistry who did a bachelor's in chemistry at the University of Oxford. He then went on to do a PhD in chemistry at the University of Oxford as well, before coming to the University of Edinburgh to become a Royal Society University Research Fellow in 1992. From there he became a lecturer in 1996 and in 2001 a senior lecturer.
So let me tell you about my career then. So I was an undergraduate at the University of Oxford, and I really enjoyed doing research in my final year project. I worked on hydrides of gallium, and was really inspired by doing research. Decided to stay on and do a PhD, or in Oxford they call it a DPhil, and spent three and a half enjoyable years working on gallium hydrides. Decided that actually I liked Oxford so much that I stayed for another 2 years doing a postdoc with my supervisor. Really enjoyed developing those techniques, publishing papers, putting out lots of results. But then eventually everybody gets tired of Oxford, and so I said, okay, let's look for something else. And I had a Royal Society Fellowship in Edinburgh, which I moved to in 1992. And that allowed me the freedom to carry out my own independent research career. I started off looking at gallium and boron hydrides, but then have changed direction, and I'll tell you a bit more about that in a moment. So I was appointed lecturer in 1996, senior lecturer in 2001, and I got my chair of high pressure chemistry in 2008. And I've done many of the roles in the School of Chemistry, so I've been a personal tutor, I've been a course organiser, I was director of teaching for 5 years, and for the last 4 years I've been head of the School of Chemistry.
Amazing. Yeah, thank you for that. So what do you currently research in?
So my research directions changed on a number of occasions. So I started off looking at hydrides of gallium and boron, and I still have a passion for gallium. Gallium is my favourite element. But I realised it was important to change research direction because of the challenges of getting funding for that area of research, but also because I was inspired one day by a colleague from the School of Physics. He came over clutching something called a diamond anvil cell, which is a small device which you can hold in the palm of your hand. And this, he said, I've got a single crystal of acetone. And I said, how can that possibly be true? Because I know that acetone is a very low melting liquid. It melts at minus 95 degrees Celsius. And you're telling me you've got a single crystal of this material. And he said, well, of course, it's under pressure. It's at 15,000 atmospheres. And that was an inspirational moment for me, because I realized actually there's a whole area of high pressure crystallography, high pressure structures, and from that moment I moved into a new direction, which was focusing on the structure of molecules, molecular materials under high pressure. So why is that important? Why would anybody want to look at simple molecules under pressure? Well, a number of reasons. For these molecular materials, often relatively low pressures are required in order to change the way the molecules pack in the crystal. And this is known as polymorphism. So pressure is a very good way of changing crystal structures, changing polymorphs. Different polymorphs have different properties, such as solubility, sometimes colour, melting point, and a whole range of other interesting properties. And so we began a program looking at more complex molecules, drug molecules, because in the pharmaceutical industry, people are very interested in different polymorphs. Different polymorphs can often have very different bioavailabilities because they have different solubilities, and so this is something that the pharmaceutical industry spends a lot of interest, time and effort into studying. And so we've had a lot of success looking at small molecules, small pharmaceutical molecules, crystallizing them under pressure. And then I went to another conference back in 2005. This was a meeting in Italy, and I met somebody there who was giving a presentation on energetic materials, polymorphism in energetic materials. Energetic materials is the broad name for things like explosives and propellants. And he showed us some of these molecules like TNT and other related materials. And I thought these are really very small molecules that are quite interesting. Can we use our high pressure techniques to study them? And so then began an area which is still very active, which is looking at these explosives and propellants under pressure. Very interesting because when these materials detonate or react explosively, very high pressures are generated. So one of the key things that we need to know then is what's the structure of these materials, not just at ambient conditions, room temperature, room pressure, but what's the structure at 40,000 atmospheres, what's the structure at 40,000 atmospheres and 500 degrees Celsius. So these are the sorts of interesting questions that we're very, very, very interested in. And that began my collaborations, I think, with the big science facilities at the Diamond Light Source, the big synchrotron source, and also the ICES neutron facility, also down in Oxfordshire. And these are enormous facilities. You get allocated a few days of beam time. The beam runs 24 hours. So this is late nights, lots of hard work, keeping the team moving, but fantastic results that you could not get from laboratory sources, and I find that particularly inspirational.
Yeah, awesome. So it looks like a lot of exciting research is developing within you, well, with you and your team. So what kinds of experiments do you do? I know you mentioned ICES neutron facility and they use beam work and stuff. So yeah, tell us the types of experiments you do in the lab and maybe outside that.
Sure. Okay. So one of the main pieces of apparatus that we use is something called a diamond anvil cell. So this contains two gem quality diamonds. These are natural diamonds dug out of the ground with two flat faces, and these form a sandwich. There is a piece of metal with a hole drilled in it, or a gasket, and we put our sample in there, usually with some pressure transmitting fluid. So this ensures that the environment is hydrostatic, i.e. the same pressure throughout, so you don't crush the crystal. And using this we can generate pressures typically up to 100,000 atmospheres. And under those conditions then we can then study these using optically. We can look at colour changes, we can look at crystal shape changes, we can use very vibrational spectroscopy such as Raman spectroscopy to look at the vibrational changes. And we can also use X-rays. So by using X-rays we can then look at the atomic arrangement of atoms in there, and we can identify some of these phase transitions. Neutron diffraction is a complementary technique. This allows us to identify light atoms, particularly hydrogen, and particularly hydrogen bonding, which is often very important for these types of materials. So what we're able to do then is to see how these structures evolve with pressure. We're able to see whether they change structure, and we're able to obtain things such as their compressibility. We're able to identify phase transitions, and we're able to sometimes to identify chemical changes which are induced by pressure. And this whole idea of crystallization under extreme conditions is really, really fascinating. It encompasses pharmaceuticals, it encompasses these energetic materials. More recently we've been looking at materials such as biofuels. So these are biodiesel, and that's important because biodiesel is a component which is in many commercial fuels that you buy. It's good for the environment, but it has some undesirable properties in that it crystallizes and freezes at relatively low pressures. So where are those pressures in the engines? Well, the pressures actually are in the injection system of the engine. So people nowadays design vehicles, engines which have got very high injection pressures. These high pressure injection systems are used to create a very fine aerosol which enhances the burning of the fuel. And the higher the pressure, the better the aerosol. But the drawback is that at the very high pressures in the injection rail, the biofuels can sometimes crystallize and block the injection nozzles. So one of the things that we've been working with in industry is to identify how these materials crystallize, what sort of pressures they crystallize at, what sort of shape crystals, whether we can address this pressure-induced crystallization and ideally prevent it, or perhaps change the shape of the crystals so that they don't block the injection nozzles. So that brings me to another area of research which is particularly exciting and where we have a very, very close industry relationship. Again, it's about crystallization, but it's not necessarily crystallization under extreme conditions. It's about using something called phase change materials. Phase change materials are materials which on melting absorb heat and on cooling, on freezing, release heat. And so a good example of that is ice. Everybody knows that ice melts at 0 degrees Celsius, and you need a lot of energy to turn solid ice into liquid water. That's good for cooling purposes, but for heating purposes we use materials such as sodium acetate trihydrate. These are the sorts of materials which are found in hand warmers. You click a disc, you get crystallization, and you get a heat generated. So these are good for something called heat pads. So what we've been doing with a local company called Sunamp Limited, who are based out in East Lothian, is to create something called a heat battery using these phase change materials based on things like sodium acetate trihydrate. And our work has been to try to make sure that these materials freeze and melt reproducibly tens of thousands of times. And this is the big breakthrough that we've had. So I'm very proud to say now that the materials that we've developed in our laboratory here are now currently in Sunamp's commercial heat batteries and are being sold throughout the world.
Yeah, that's absolutely amazing to hear. Congratulations. So what types of results are you seeing from your research, first with like pharmaceuticals and using explosive materials, and then with your work with the heat batteries?
Okay, so for pharmaceuticals, what we demonstrated was that pressure is a very effective way of screening for different polymorphs of drug compounds. And as I mentioned earlier, polymorphs have different properties, such as solubility, bioavailability. And so this allows the pharmaceutical companies to very rapidly identify potential polymorphs, and therefore they're able to satisfy the regulatory authorities that they've fully explored the phase space of these materials. In terms of explosives and propellants, it allows us to understand the behavior of these materials. And actually one of the things that we're currently working towards is the design of materials which are much safer, much less sensitive to accidental initiation. And so that's a real driver. By understanding their high pressure behavior, we're able to say, well, okay, one of the reasons this is a sensitive material is because of this particular structural feature. So can we design this structural feature out or modify it so that it becomes a safer material and less prone to accidental detonation or initiation? In terms of the heat storage materials, probably one of the big benefits there has been the understanding of how to make these materials which will reproducibly cycle tens of thousands of cycles. And that gives the company, Sunamp in this case, the confidence that their heat batteries will work for many tens of years. And that's really important if you're going to install one of these heat batteries into somebody's house. It's also very important for investors in the company to know that actually there is a solid product here a product which has been fully tested. And what that means then ultimately is that this heat battery technology is having two effects. The first effect is it's reducing carbon dioxide emissions, which is clearly a very good thing. And secondly, it's also helping to reduce people's fuel bills. And that has an impact upon fuel poverty. And that's something that I'm very, very passionate about. 25% of Scottish households suffer from fuel poverty. That means that people have to make choices about whether they heat their homes, whether they cook their dinner, or whether they have hot water, or whether they even buy food. And this is really, really important, something a challenge that we really should be addressing. And the technology that's been developed in collaboration with SunAmp is starting to have a major impact upon tackling that fuel poverty.
Yeah, that's amazing outcomes from your research. Like for all of them, it seems like it's really going well, to put it simply, and developing quite a lot. So where do you think the future of your research is kind of heading? Do you think you can make further developments in each of these areas, maybe even branch it out commercially, or as you say, just extend it further?
Okay, so I think the pharmaceutical area is something which has been a bit slow to take off. I think the pharmaceutical industry sometimes is rather conservative and it's rather sometimes reluctant to adopt new technology. But I think we've now demonstrated quite convincingly that this high pressure approach is a very effective one. And one of the nice things that's happened recently is that we've secured additional funding from one of the Engineering and Physical Sciences Research Council to purchase a state-of-the-art diffractometer, X-ray diffractometer. And that's going to be installed in the Centre for Science in Extreme Conditions, which is based on this campus at King's Buildings. And that will allow us to make very, very rapid measurements, single crystal determinations. And that will allow us to essentially to increase the rate of screening of these compounds. And that means that we will be in a much better situation for speeding up the screening and identifying potential polymorphs. And so that's an area that I'm quite interested in working more closely with pharmaceutical companies, perhaps even commercializing, because we have a rather unique set of expertise and rather unique tools here to do that. In terms of the heat storage, so one of the areas there is most of the work we've done so far has been domestic hot water storage. But in fact, there are much bigger challenges and actually much more rewarding challenges to be obtained as we move to higher temperatures. So this is 150 degrees Celsius up to 600, 700 degrees Celsius. There, the energy density of your materials is significantly higher. You've also got much higher temperatures, and that means that you could potentially use this to generate steam, which you could then use in power generation, electrical power generation. You could also use it for replacing night storage heaters and also for heating applications on automotive vehicles. So there are a range of different applications there. So our movement in that direction then is to move towards higher temperatures with higher energy densities.
Yeah, it sounds like there's very practical applications to your research currently. Do you see the reward of then seeing your research being used maybe outside of a lab and such?
So I'm a great believer in fundamental, curiosity-driven research. This is what attracted me, and I think this is one of the key things that excites many scientists, particularly chemists. But at the same time, it's always good to have the knowledge that your fundamental research is underpinning research or development of products which are being developed by industry, and ultimately having a benefit for wider society. So if you like, this idea of the socio-economic impact of research I find really exciting, and it's becoming an increasingly important aspect. Many of us are funded by government and ultimately the taxpayer, and so actually being able to demonstrate the value of your research, I think, is really important. But it's also incredibly satisfying knowing that something that I've developed or my team has developed is making a difference in people's lives.
Yeah, absolutely. It sounds so satisfying, the fact that you can make this difference from what you're researching and researching something that you are interested in, and you have that passion behind studying it, which is really nice. So with the different aspects of your research, how do they fit in with maybe the bigger picture of chemistry? Do they help with other research going on currently?
Yeah, so I think one of the things I quite like, and hopefully you will have picked up from my research, is I'm interested in a number of different areas, and I think that's a good thing to embrace, because it allows thinking from one area to move into an adjacent area. So this idea of adjacent areas of research. So, and I think that translates into interacting with colleagues and collaborating with other colleagues. And so I'm very pleased when I have discussions with colleagues and I'm able to contribute new ideas to their research, but equally then they can contribute new ideas, new concepts to my research. So I think it's one of the dangers potentially of being a researcher is always to become too narrow and not be aware of what's going on in other fields and indeed other disciplines. So I like talking to physicists, I like talking to engineers, I like talking to biological scientists, and I think this is really important. And it's often at these boundaries of disciplines that the really exciting results, discoveries occur. And I think it's very interesting that a lot of the Nobel Prizes that have been won recently are people who have actually switched discipline or are working on the boundaries of the different disciplines.
Yeah, absolutely, exactly. Because, well, from doing these podcasts, I have kind of spoken to people who study biophysics, which are two seemingly contradicting sciences, but they come together and the results can be amazing. So I completely agree with you there that maybe becoming more aware of the different sciences or different types of sciences and researching them is very important for maybe your own research to make these kinds of breakthroughs.
Yes, I agree.
So I know you mentioned about studying biofuels and the way that they crystallize in engines. Do you have an interest in more environmental chemistry? I know it's quite a big topic in climate change and maybe reducing our plastics and being more environmentally friendly. So do you have that thinking when you're approaching your research? I know some of it doesn't apply, but other aspects do.
Yes, I think that's one of the things that motivates me, and I think climate change undoubtedly is the single biggest threat to this planet, and we have a moral duty as scientists, as chemists, to tackle that. And that's one of the main drivers why I've been so interested in the heat storage batteries, because everybody tends to think about electricity and transport as being one of the main users of energy, but actually heat is by far the biggest of those. 42% of the energy use in the UK is to do with heating or cooling. And so by tackling this rather perhaps forgotten aspect, we can make a significant impact upon reducing environmental emissions, CO2 emissions. So one of the challenges today is sustainable use of resources, and this I think is something that is going to become increasingly important. We have become very much a consumer-driven society, and we're still going to have to make use of many of the materials, but we have to do that much more responsibly. We have to do that using much more recycling. We have to extract our minerals. We have to extract our metals, our oil-based products in a much more sustainable way. And so I think that's one of the grand challenges for technology, but I think particularly a grand challenge for chemistry. Chemists are very creative people. We make molecules, we design molecules, and so by thinking carefully about how we source the raw materials, the types of processes that we use, are they safe? Are they non-hazardous? To what extent are they sustainable? It makes a real difference in what we do. And I think, looking back at the history of chemistry, it hasn't always, particularly chemical manufacturing, it hasn't always been very green or environmentally friendly. People have not thought about the environment. And so I see this as a huge opportunity for chemistry to make an impact in this area. The issue of plastics is a fascinating one. It's been brought up, and I think it's very interesting to see how the debate is moving. And I think one of the things that's very important to remember is that plastics do have their uses, and actually you have to do some quite careful analysis to see whether plastics should be in a particular supply chain or not. So one of the important points about plastics is that they are fantastic packaging materials, and everybody complains about packaging, but actually they are very lightweight, and you can actually package an awful lot of weight in this way. And so why is weight important? Well, if you think about transportation, the more weight you transport, and if that weight is partly due to packaging, then you end up actually having higher greenhouse emissions. So I think there needs to be some careful consideration as to not just to say all plastics are bad. Some plastics are bad. We can do much more about recycling of plastics. We should be much more thoughtful about how we use plastics, and in particular how we dispose of plastics. But I think there is a role here for chemistry, I think, and chemists to have that help inform that debate about whether something is a good thing or a bad thing. And usually the answer is that it's not black and white. There is this area of greyness, and you have to have a good understanding of what the factors are which affect that particular process.
Yeah, you're right. And chemistry is probably one of those subjects that do have to maybe think about, as you say, where they get their metal ores or oil-based products from in probably a more sustainable way in the future. And yeah, it's not always black and white. As you said, there is this heavy grey area that we probably still need to figure out, and it'll be exciting to see where it kind of goes in the future and how scientists, researchers factor it into maybe what they're doing currently. So I want to kind of pick up slightly randomly with your work on explosives. I kind of just was wondering, what kinds of things can your research be applied to? I know you mentioned less accidental initiations of explosives, but kind of is there any other areas in looking to the way that these structures change under high pressure and temperature?
Okay, so there is the fundamental curiosity about what happens when you squeeze these molecules. How do they respond? And that's is a fascinating aspect. We shouldn't forget that most explosives are actually used in the mining industry or demolition. So it's not so actually a relatively small amount of these materials are actually used in military applications. And the transportation and handling of explosives is something which has huge implications for health and safety. And so the work that we're doing in high pressure studies of these materials informs us about how we might be able to design materials which are potentially less hazardous, less prone to accidental initiation, and therefore easier to transport. Thinking about how do we make things safer, how do we make the things actually also greener. So they're actually one of the interesting areas is how do we remove lead-based materials from explosives. So a lot of the initiating materials are lead-based. They've been used for 100 years. And so lead is no longer an acceptable material to use in a whole range of applications, including explosives. So one of the programs that we're currently looking at is how do you switch out lead for other metals or non-metals which are much less toxic. And again, the high pressure work that we do gives us insight as to how these molecules actually interact just before they react and explode. and so this high pressure studies allow us to say, well, perhaps we should be looking at this particular class of compounds rather than this particular compound, or this particular structure is a good structure for getting the performance that we need, but at the same time maintaining the safety.
Yeah, it sounds so cool that you're almost making your own chemical structures. Well, that's what it sounds like to me. And through this research, it kind of sounds amazing that you can manipulate these structures in such a way.
Well, I think you put your finger on it. This is one of the things that excites chemists, not just me, but many of my colleagues who make molecules. There is a very strong creativity. So we like to make new molecules, look at the structure, we're very interested in structure, and correlate that structure with properties. And if you know that structure-property relationship, then it allows you then to design. And eventually it will be great to actually almost end up dialing a particular molecule. I want a molecule or a material which has got the following properties. Can the chemists make that? Now we're a long way from that, but we have a very powerful toolkit. But it would be ultimately that's the future of chemistry. Somebody says, I want this particular material with these particular properties, and then the chemists say, actually, this is what you need.
Absolutely. It's, as you say, it's kind of like just the curiosity, the creativity behind it as well is something that would, for me, that would be where my interest would lie as well. So what interests you so much about high pressure chemistry specifically?
That's a very good question, and I think it is inspirational actually, because high pressure has such an impact, such an effect on all types of matter. So, for example, at the bottom of the ocean, bottom of the Mariana Trench, there are pressures there of over 1,000 atmospheres, yet there is still life survives underdown and indeed thrives at these pressures. So what is it that's allowed life to evolve? And actually, if you look in detail, you start to see it's the way the proteins that have been formed from the different amino acids, right? And there are particular amino acids, then particular sequences of them, which are particularly prevalent in these organisms which live at very high pressures. I think the other, as we move up in the pressure scale, we start to see changes in crystal structure, and that's what excites me about the different polymorphs. But as you go to even higher pressures and start to squeeze things, the minerals, you start to see, of course, you take graphite, high temperature, high pressure, and you turn it into diamond, right? And that's an amazing transformation, which has gone on in the earth for millennia, and is still going on within the earth. And the fact that we can reproduce that in the laboratory and make diamond from graphite, I think is really, really exciting. And then as we go to higher pressures still, we start to see how many materials, many elements can become metallic. So iodine will become metallic, oxygen will become metallic, and even hydrogen will become metallic. Why is that important? Well, it starts to explain some of the mysteries of the universe and the solar system. Why is it that the gas giant Jupiter has very, very strong magnetic fields? Well, the concept, the idea is that potentially it has a liquid metal hydrogen, so metallic hydrogen core, and this is the thing which is causing this very high magnetic field. So it starts to give us insight into our surroundings, but also the wider solar system and the universe. And I think what attracted me originally to this was the fact that you could generate such different crystal structures with such different properties simply by applying pressure.
Yeah, absolutely. And I like how it's not a simple concept, but it's like one area of chemistry can be applied to so many different other areas. I love how it just goes so much further than anything that you kind of find on face value, almost. I also want to ask, what kind of excites you or interests you in becoming a researcher? Because you've done it for quite a number of years now, and as you say, you kind of just went into PhD and kept going.
Okay, so I remember my first result, which was during my final year of my undergraduate degree, was doing a project, and I'd been working very hard for about 4 months, trying very hard to get the evidence for this molecule, gallium hydride. And I remember vividly that we had time on an instrument, the NMR spectrometer. It was midnight, and I'd worked very hard to make a very small amount of this material sealed into this NMR tube. I had to keep it cold, below minus 20 degrees Celsius, otherwise it decomposed. And I put that in the NMR spectrometer, and we ran the spectrum, and there were 2 peaks in the ratio 2:1, which is exactly what we were hoping for. So this was the first time anybody had made this molecule, after many, many years of struggle and false results which would subsequently prove wrong. And finally we had the 2:1. And I was the first person to see that result. And my word, that just made me so excited. I wanted to tell the world. I was going to ring up my supervisor, but I thought it's 1 o'clock in the morning, he'll be asleep. I wanted to tell my dad, but 1 o'clock in the morning, he's also asleep. So I had to wait until the next morning to go in and present the spectra to my supervisor. So that was that element of working hard, struggling against lots of barriers, overcoming challenges, and then finally getting a result that nobody else had ever seen before. And that, I think, is the motivator for me and for many of my colleagues, be they in chemistry or any other discipline. It's that discovery of something new that nobody else has ever seen before. And I see that spark of enthusiasm in undergraduate students who do projects, and of course I see it in PhD students, and that's the thing which is really motivational. And that's the point at which I decided I wanted some sort of career in research. I didn't initially think it was going to be academic, and I certainly didn't imagine myself being a professor of chemistry. I decided that I wanted to do a PhD, and then I moved into the postdoc, and then I decided I'm really enjoying this. I would like to do a research fellowship, and then subsequently the lectureship. But I think it's not just about the research. The academic job is also about teaching, and I enjoy teaching. I get a lot of satisfaction. And again, it's the satisfaction of getting across perhaps a difficult chemical concept to a student, and then suddenly they get it and their face lights up, and that's a very rewarding experience. And so that the academic job has been particularly rewarding because it gives me freedom to do curiosity-driven research. It gives me the opportunity to translate my research into applications. But it also allows me to try and enthuse and educate and inspire undergraduates and postgraduate students.
Yeah, and it's amazing to hear that you love your job so passionately, because that's kind of one of the goals, I guess, in finding a career that you do love and you get to do exactly what you want and you find it so rewarding. So it's fantastic to hear about that.
Mm-hmm.
And I have a question that I thought of at the very beginning. You mentioned that you really liked gallium in your PhD. Why are you so interested in that particular element?
So my undergraduate project and my PhD was all about the hydrides of gallium. And gallium is a fascinating element. It's very silvery, very shiny. It melts at 28 degrees Celsius, and so it's actually almost a liquid metal, only slightly above room temperature. But it's, I think, also partly because I studied gallium chemistry, so I know all about the chlorides of gallium, the hydrides of gallium, the borohydrides of gallium, and so you develop almost an affinity, a love affair with this particular element. And remarkably, I have not done very much subsequently since moving into high pressure on gallium or gallium compounds. But one of my ambitions is to move back into gallium chemistry and start to do some experiments on perhaps gallium hydrides or gallium halides. But I think that perhaps that is that first love which is inspired by your early research. You get an affinity for particular elements. And I think if you ask any chemist do they have a favourite element? They'll almost certainly say yes. And quite often it's the one that perhaps they started their PhD on, or one which gave them a significant body of research work.
Yeah. Well, one of the last questions I want to ask you is, do you have any advice for undergraduates, maybe thinking about doing research in the future or kind of unsure about what they want to go into studying chemistry right now?
Absolutely. I think perhaps the best bit of advice is to try it, right? So try experience research, because you can read all about it, but actually there's nothing like doing it. I think be prepared that things don't work. These are not like well practiced undergraduate practicals. Some things will not work. They will fail for different reasons. And if it were easy, it would have been done before. And this is a message I give to my PhD students when they're struggling to get results. If it were easy, somebody would have done it before. I think don't just restrict your ideas of research to academia. There is a whole range of interesting industrial research out there, people in industry tackling really very challenging problems with real world applications, and I think sometimes that's a real motivator as to what it is that you're going to do. The piece of work that I do as a researcher, be it in industry or in academia, is going to have an impact upon other people, and I think that's really important.
Yeah, that's great advice, thank you. And especially I love that saying, if it was easy, someone would have done it before, because that is kind of true, and you could probably maybe lose sight of that if you aren't getting the right results and you're like, wait, hang on, like I'm kind of doing something someone hasn't done before. So yeah, that's absolutely brilliant, thank you. And my very last question, unfortunately, because it's been a great interview, so I kind of want to keep it going, but my very last question is, do you have an inspirational book or article for us to share?
I do, and it's related actually to my previous comment, and it's called the Periodic Table by Primo Levi. So this is the International Year of the Periodic Table. Primo Levi was an Italian chemist who was Jewish and therefore was rounded up by the Nazis and ended up in a concentration camp. I can't remember where it was. Anyway, he ended up in a concentration camp. He was a chemist and used his chemical skills actually to help him survive during the concentration camp. But he wrote in his book, he selects a range of different elements and tells stories around the different elements. I find it an inspiring book, and I read it as an undergraduate when I was doing my project, and I would thoroughly recommend it to anybody who has even a slightest interest in chemistry. You don't have to be a chemist to read it. It's a very accessible story, and it gives you some of the thoughts and insight into how do chemists think. What do chemists do? There are some wonderful short stories in there. But actually, one of the opening quote of that book is something that Primo Levi used, and the quote is actually a Jewish proverb, and it says, "Troubles overcome are good to tell," and I think that's actually sums up the research process. If you can overcome the challenges, the barriers, and then it's so great to talk about them. So that's my motto: troubles overcome are good to tell. And in fact, it's actually, I borrowed that quote and put it in my undergraduate project report because I was so excited by the troubles that I'd overcome, and I wanted to tell the world about it.
Yeah, that's an amazing recommendation. Thank you, especially that quote. That's a very good life motto to live by.
Mm-hmm.
Yeah, so thank you so much for being on this podcast and for taking the time to be interviewed. It's been absolutely amazing.
Thank you. It's been a real pleasure. Thank you so much.
So thank you for listening to this week's episode of Delving into Academics, and I hope you found it interesting. Please like, review, comment and subscribe wherever you're listening to this. And if you want to find out more about the researcher, I will have their university website page linked in the description. See you in 2 weeks for another episode.